something that I certainly want to know more about in my new role here, Trade Me. And it's something that we kind of take for granted. But a lot of us don't actually know what's going on behind the scenes, which explains why we sometimes get counterintuitive results with things. So I'm absolutely thrilled to have Ben talk about this and invite Ben to take over the stage and walk us through what we should be doing.
Yeah, and please feel free to type your questions into the chat window. We'll interrupt, when it makes sense, and there will be some time at the end for Q&A. So, awesome. All right, over to you, Ben. Thank you. If you could present your screen.
Thank you so much. Hopefully you all can already see my screen here. Thanks for your time. I am excited about this. We're going to talk today about how Power Query thinks. How does Power Query's mashup engine process the expressions you write? Query folding is one key concept, where behind the scenes the engine may transform part or all of your IM code into the data source's native query language, then ask the source to execute that query. Streaming, though perhaps a less familiar term, is even more fundamental. It describes how table, list, and binary data flows between functions in IM. Let's take the mystery out of these two terms, but before we get to them, we'll lay a foundation of basic concepts about how the Power Query language works. Altogether, the goal of our time together is to give you an understanding of how Power Query thinks, so you can write more efficient mashups, are better positioned to debug problems, and can avoid unexpected variability in results. Let's get going. Foundational concept number one, Power Query, IM, is partially lazy. Here we have a let expression. In the result clause of this expression, that's the bit of code after the in, we see that only the value from variable A is needed to produce the requested output. What about variable B? Is its expression evaluated? Is call service B invoked? Well, no, because in IM, let statements or let expressions are lazily evaluated. If a variable isn't needed, its expression isn't evaluated. This is great. It means IM tries to do the work that's needed, but in this case, at least, not more work than's needed. Turns out the same thing holds true for record expressions. Here we have a record inside of a let expression, and we can see that only field A's value is needed. Since record field B's value is not needed, its expression is not evaluated. Now, if you look at this record expression, you might see that we could refactor it. We could get rid of the whole let expression and just have a record expression, right? Now look at this refactored expression, if you would, and compare it to the let expression we started with. Don't they look quite similar? Well, not only are these two expressions similar, but they're more or less identical behind the scenes, because in Power Query, let is syntactical sugar for an implicit record expression. So this means that if you understand how records work, you understand how the let expression works. And everything you know about how a let expression works applies to records. Now, we've said that Power Query is partially lazy. Partially implies that it's not always lazy. The principal exception to its laziness are function arguments. In the IM world, function arguments are eagerly evaluated. In this let expressions result clause, the function do something is invoked. When it is invoked, the values of variables A and B are passed in. Notice that the values are passed in, which means they need to be computed before the function is invoked. So when do something is invoked here, both service A and service B have to be called in order to produce the values that do something needs. Now, you may notice, though, looking at the definition for do something, that only one or the other of the two arguments value is ever needed. but we've had to compute both of them to invoke this function. Now, what if calling each of these services cost money? Or maybe it's time. It just slows things down to call two services if you only need to use the value from one. Is there a way we can change this behavior so that M is not eager here, but it's lazy? Well, let's do a little refactoring. Notice what we did here. We changed the expressions for variables A and B by removing the function invocation parentheses. That was at the end of each of those expressions. And we moved those parentheses inside our do something function and appended them to the end of the two variable references. So now what happens when the let expressions in clause is evaluated? Well, the values for A and B still need to be passed in and are still eagerly evaluated because that's how M works. But what are those values this time? They're not the values produced by calling service A and service B. They're the references to those two functions. And it's only inside the do something function that the if statement chooses which of the two services to invoke. You see that in the then and the else. Then return the result produced by invoking A, or else return the result produced by invoking B. So M is partially lazy, but not always, with the principal exception being function argument evaluation. Another foundational concept about Power Query. It's immutable. This pseudocode example here is not Power Query. You can see that we set a variable x to the result of calling service A. We then add 3 to x. Then we check x's value and set it to something else. We mutate the value of x. With M, you can't do this, because with M, when you assign a variable a value, that value is fixed. For example, in this expression here, you see we're producing a list that consists of 2 items. And the expression for each of those 2 items references variable A. How many times is the expression for variable A, that is call service A, invoked or executed? Exactly 1 time. The first time its value is needed, call service A is invoked. The value that's returned is saved into variable A. And then anytime variables A's value is needed during the current execution of the Power Query, that saved value is returned. So even though this list expression needs A's value twice, the expression behind A is only executed once. This behavior holds true for error messages as well. If call service A didn't return a value, but instead raised an error, that error will be saved into variable A. And each time variable A is accessed subsequently, that error will be re-raised. So for let expressions, and by extension, record expressions, since a let expression really is just a record expression in disguise, variables and record fields are immutable. What if we don't like this immutability? What if, for some reason, we really want it to call service A twice? Well, don't save its value in a variable or record field. In the second expression on the screen, we create a list with 2 direct invocations of call service A. No variables, no record fields are involved, so it gets invoked twice. M is immutable. But there's an asterisk by the word immutable. It's true, it is immutable, but there is more that's going on than meets the eye. Based on what we've covered so far, when you look at this expression, you might think, well, let's figure out what we think it's doing. We know that since M is lazy, it only does as much work as is needed, at least for let expressions and records. So to figure out what M's doing, we should go start by looking at the result clause. That's the bit again after the in statement and work backwards and see what's referenced. So the result clause references the value of first three. So based on what we know so far about immutability, we would imagine perhaps that first three's expression is evaluated. And to do that, see cause table first in, and it passes in the value of filtered. And since function arguments are evaluated eagerly, let's go figure out the value of filtered. Okay, so that's table select rows. And another variable reference, source. What's source get data? Okay, so based on what we know, it might seem like that first get data is invoked and all the data it returns is saved into variable source. And then that value is passed into table select rows and all the data that function returns is saved into variable filtered. That set of rows is saved, is passed into table first in, and all the rows returned by that function invocation are saved into variable first three, and then that's returned. This is not how Power Query works. Let's call what we just described the simplistic approach. Here on the screen, you can see across the top, we have the three steps we saw before: source, filtered, and first three. And with the simplistic approach, well, it works. It produces the expected results, but it has some downsides. What if source contains, I don't know, 1 trillion rows? Well, we've got to pull all that trillion rows down and save it somewhere, right? And then we pass it to filtered, and filtered does its filtering, and we got to save those rows somewhere. First three, again, we got to save those rows somewhere before we can hand them out to the requester, to the user interface. So this means that we have to have local resources to hold all the rows in source, which means that if source contains a lot of data, we might not be able to execute our Power Query expression because maybe we don't have local resources to hold 1 trillion rows in memory or on disk. But there's also another downside I'd like to draw our attention to. How many rows does this expression need to produce? Well, 3, or maybe less, at most 3. Chances are that those 3 rows can be produced without pulling all rows from source. I can't guarantee that, but maybe we really don't need to look at all 1 billion rows from source to find 3 qualifying rows to return. Maybe we just need the first 3 rows from source or the first couple hundred. But there's no shortcut here. We still have to pull all rows, so we may end up doing way more work than we need it just to produce 3 rows. Again, this is not how Power Query works. Now let's get into how it does work, and we'll start with streaming. With streaming, what happens when that let expression is evaluated? Each variable is set to something and set immutably, but that something is not the actual data. It's rather a handle or a promise or an iterator that can be used to produce the requested data when needed. So the variable first 3 holds a iterator, which references a chain of function calls that can be requested to produce rows. And let's look at what happens with how that works. So a request comes in to the iterator held in variable first 3, asking for a row. And first 3 says, okay, to fulfill this request, I need a row. And it turns around, it's holding a reference to filtered, or to filtered's value, which is another iterator. And it asks for a row, and filtered, to produce that row, it looks at what it's holding. It's holding a reference to sources, an iterator for source, and it asks that iterator for a row. And source does whatever it needs to produce a row, and it streams, hence the name streaming, it streams a row to filtered. Filtered looks at that row, says, okay, I have this test expression to see if this row qualifies. It passes the test. I'll hand it to first 3. First 3 says, yay, I got a row, and it hands it out to the requester. The requester, the user interface or whatever's executing this expression says, hey, I need another row, please. First three says ask filtered for another row. Filtered enumerates source asking for another row. It receives a row. Filtered checks that row against its test expression, and it's rejected because it didn't pass the where clause, so to speak. So filtered still has this outstanding request from first three for a row. So it turns around and asks source for another row. Source sends that row, and thankfully this time it passes the filtered test. Filtered hands it to first three, and first three hands it on out. And this process repeats where rows are iteratively requested and then streamed until first three has either returned three rows or until it's iterated through all the rows and hasn't found three qualifying rows, and it one way or the other, execution ends. This is streaming, and it is the foundation of how Power Query processes table, list, and binary data. Now, you'll notice key takeaway here that rows flow between steps one at a time. Doesn't mean, though, that a step only holds one row at a time internally. In fact, data sources are a good example of a function that might need to hold more than one row at a time. If you call a web API, you might get back 100 rows, right? So perhaps when source here is invoked, it calls web API, it gets the first page of rows back, it's 100 rows. So what does it do? It buffers that 100, and then it returns the first row. And then the next time it's asked for a row, it pulls the second row and returns it, and so on and so forth. Then it does that until it gets through that whole buffer. And then it turns around and asks the web API for that next page of records and repeats the process. Again, rows flow between steps one at a time. And in this case, filtered in first three don't do any buffering, but source did, and that's common for sources. The other key thought before we leave this slide, Im is immutable. The variables in a let expression, once set, cannot change. But for stream data, those variables are immutably set to handles that allow rows to be retrieved on demand, not the actual rows that are retrieved. So we avoid the problems we saw with the simplistic approach of needing local resources to hold all rows that need processing, or all rows from source, and of needing to pull all rows when maybe we only need to look at the first few to get their desired results. With streaming, order matters. If you would look at this set of steps here. These steps are ordered where the last step would be the step referenced by the result clause in the let expression, and then that step reference that's filtered, and filtered references source, sort, and sort references source. So let's think about this here. If source returns 1 trillion rows, okay, so the host application asks filtered for a row, filtered turns around and asks sort for a row. But sort can't just grab one row from source and return it because it needs to sort the data, right? I mean, unless it somehow knows that the data is already sorted and will assume it doesn't. So what does sort do? It has to ask source for 1 row, 2 rows, 3 rows, all the rows. And then it has to buffer them inside it. And then it has to perform the sort. And only then can it return the first row, the row that filtered requested. This is still an improvement upon what we saw with the simplistic approach, because with the simplistic approach, every step's rows were saved locally. Here, only steps that need to save rows locally. But it does raise the question, is there any way we can improve on this? Because here we just had to have local resources to save the trillion rows returned from source. Well, absolutely, there's a way we can improve on that because order matters. Now here, I could reverse the order of steps 2 and 3 and produce the exact same results, but potentially use an incredibly smaller amount of resources. All right, so what happens here? The execution starts, sort is asked to produce a row. Sort needs to get all rows from its upstream to produce that single row. So it turns around and asks filtered for a row and does that iteratively until it gets all rows from filtered. Filtered, of course, is iteratively asking source for all its rows, but it's only giving sort the filtered rows. So it pulls 1 trillion rows from source, but it filters that set down to only 50,000 rows. That's all that sort now needs to buffer. There's a whole lot less resources required if you're buffering 50,000 rows as we are on the right than on the left where we had to buffer, what was it, 1 trillion rows? So order matters with streaming. Here's a gotcha, though, to be aware of with streaming, and that's restreaming or multiple iteration. You'll see in this in clause, in the result clause here, we're producing a list that calls list sum twice. Now, you'll probably say, why would I write code like this? Probably wouldn't ask for a list to be summed twice. Well, you're right. It doesn't seem to make a lot of sense. But you might write code that indirectly does something like this. What if you want it list sum and list average? Well, how do you compute an average? Well, behind the scenes, you need a sum, right? At least that, something like that, right? So you might write code that does something like this twice. And it might surprise you if you execute this expression to see that the two sums in some cases might not equal. Wait a minute, I'm summing data from the same source, the same column twice, and I'm getting 2 different amounts. What's going on? Well, remember that variable source is just a handle that can be iterated to get data. So when the first list sum executes, it iterates all the rows from source and comes up with the sum. When the second list sum executes, what are we asking it to do? Iterate all rows from source to get the sum. Well, what if source has changed between those 2 iterations? What if a row was added or taken away or updated? We could end up with list sum producing 2 different values here. Now, sometimes behind the scenes, it's possible an IM optimization might see this duplication in theory and help us out and only sum it once, but we shouldn't count on that. That's not guaranteed. We've asked it to sum twice. Streaming is in play. We should expect it to iterate all the rows from source twice. So how do we work with this? In this simplistic example, you could add another variable in the let expression, assign it the value of list sum, and reference it twice in the output list. But for a more generic solution, we might turn to buffering. Here we're showing table buffer. If we were working with list data or binary data, there are corresponding buffer methods for those 2 data types. You notice though what we did here in list sum, we changed the column expression or the list, the argument from referencing source to referencing the buffer. So what happens? Well, in the buffer grabs all the rows from source and buffers them locally. Then anytime that buffer is accessed, anytime a new attempt at streaming rows from that buffer is begun, that request is serviced out of the buffer. So when the first list sum executes, it's reading from buffer and it reads the first row, the second row, the third row, and so on and so forth. Then when the second list sum is processed, it reads from buffer. And its iteration, of course, starts with the first row and counts through them, but it's the same set of rows because it's reading out of a buffer. So source is only has data pulled from it once. It's buffered locally. Keep in mind, for those of you, just keep in mind that buffering is shallow. It's buffering the top level. If you have a table containing tables, which contains rows and so on, it's buffering one level. Now here, we're kind of forcing this variable buffer to behave in the simplistic manner that we saw in our simplistic approach, but you're choosing when this happens. You still have to have local resources to be able to do the buffering, but you're in control. You can apply this tool when you need it, being conscious, of course, of the cost. Restreaming, it's a got you to be aware of multiple iteration. Now, here's this expression we saw a few minutes ago. And we're excited because we now, with streaming, that we don't have to cache all these rows locally. We don't have to buffer them all locally. But we still have the downside. We have to potentially pull a whole bunch of rows to produce the desired results. Sooner or later, you're looking at this with a coworker, and your coworker says, you know, hey, the source here is a database. Database server has indexes. It does things in memory with paging. I could write a SQL query. It would pull exactly the 3 rows that are needed. It would do it blazingly fast. We wouldn't be streaming thousands or tens of thousands of rows or hundreds of thousands of rows so that Power Query can process it. Maybe I should just write a SQL query. You wrap it in the little bit of Power Query that's necessary to execute a native query, and we'll call it good. Thankfully, Power Query may be able to help you out here, because with query folding, Power Query can take an expression like the one on the left and behind the scenes rewrite it into an expression like the one on the right. So instead of you needing to manually write the SQL statement or the native query or request, Power Query writes it for you. So you're getting the best of both worlds. You are writing in the beauty of Power Query, but you're getting the execution efficiency of the native data source. That is really neat. This is what query folding does. Let's think about it though. Be aware of when we're working with query folding is not every function call is foldable. Which function calls are foldable depends on the mashup engine version, on the data connector, and it can even depend on the particular data source the data connector is pointed to. And like streaming, order matters when folding. So here we've got an expression where the first 2 steps are foldable and the 3rd and 4th are not. So what happens? The first 2 get folded and the 3rd and 4th don't. So streaming comes into play here. I'd encourage you not to think of this as streaming or query folding, but streaming or streaming plus query folding, because whatever isn't query folded is still processed with streaming. So here's another set of steps. We've got 2 foldable steps, a non-foldable step, and then a foldable step. So what happens? The first 2 steps are going to be folded because they're foldable. The 3rd step obviously can't be folded because it's not foldable. But we can't fold the 4th step because what's before it, the 3rd step, isn't foldable. Is there hope? Well, you might be able to rewrite the expression to reorder steps so that you have 3 foldable steps before the 4th step. And perhaps Power Query, the mashup engine, will help you out, because it can analyze your Power Query expression, and if it determines that steps can be safely reordered without affecting the result return, behind the scenes it might do a little query rewriting for you and reorder those 2 steps so that all 3 foldable steps can be folded and just the one that can't isn't. Now, this said, I'd encourage you not to expect this to happen. It's a bonus. Write code that's performance optimized when appropriate, with things in the right order. And we'll talk more about that in a little bit. And then if you miss something and Power Query's optimization process helps you out, bonus, that's great. So with Power Query, order matters, but sometimes IM helps you out. Little insider tip, this optimization can take place even when there's no folding, even when there's not a data source involved. It can also do things, as a side note, like if you add a column and then later on remove that column, it may be able to detect that and not process the add column expression because it knows those results aren't needed.
Sorry, Ben, just a quick question. Will we know if it's helped us out? Will you cover this a bit later on?
Could you repeat that there?
Will we know if it's helped us out? As in, if it rewrites our query, can we tell easily?
Let's jump into that question because we'll jump back here real quick. So we're talking, I'm suggesting that order matters with query folding, order matters with streaming. All right, I tell you what, let's hold that. Can I hold that question and we'll get into it in a minute? Because we've got one other piece to cover on that.
Sure.
Sorry. Thank you. All right. This brings us to privacy levels. This let expression here. What are we doing? Well, we are pulling data from A and we're filtering it. We're looking at A's ID column and we're finding all the rows where those IDs are contained in B's filter ID column. Now, this certainly valid, it works. But what if A contains a whole lot of rows, and let's say B contains very little data? Maybe there's only 4 filter IDs that B is going to return. And if we applied that filter to A, we're going to get, let's say it's 4 rows out of A, right? Now, A contains 1 billion rows. B is going to filter that down to 4 rows. We still got, with streaming, would need to pull all billion rows from A so that they can be filtered locally. Query folding, as we've covered it so far, isn't going to help us out here because the query folding we've covered folds things back to source, but here there's 2 sources involved. We can't fold this into one query. Well, it turns out query folding does offer something that we haven't covered yet. Query folding might pull the data from B and write it into the query sent to A. So here you can see that in our native query that there's a where clause. And in that where clause, we see the 4 values from B. So again, this is kind of giving us the best of both worlds. Power Query figured out how to cross these A and B to write a native, do the native queries in the right order to get what we need it from B to A, so that A is only sending us the 4 rows we need instead of needing to stream them all to do the filtering locally. This is exciting, also dangerous. What if B is a list of highly proprietary strategic data points, and A is a publicly accessible data source that's run by your chief competitor? Do you want to write values of highly proprietary data into queries sent to your competitor? I don't think so. The sole purpose of Power Query's privacy levels is to control whether data from one source can be folded into another. Now again, remember the expression on the right can be executed without query folding. Query folding is an optimization technique. It's not necessary for what's on the right to be executed. So what privacy levels do is guide the mashup engine into knowing whether the sources are safe to combine. Quite simple. So what what privacy levels do guide query folding. Now, to the question we had a moment ago, this will segue right into that, is when is query folding occurring? If you go into Query Editor and you right-click on a step, you'll see a pop-up menu. And down the bottom of that menu, there's a View Native Query option. If that option is active, if it's not grayed out, you know query folding is taking place. If it is grayed out, you don't know whether query folding is taking place. As it turns out, in this case, the 3 steps circled in red were optimized by the mashup engine. You know, they were put back to back by the mashup engine. It reordered that 4th step, sort it rows, and put it before add it custom. And unfortunately, though, the UI doesn't know how to follow this. So when I right click on sort it rows, the UI can't show me the native query, even though there is a native query for sort it rows. Unfortunately, currently, there is not a good authoritative way to tell whether query folding is happening other than looking at the actual queries or native requests being sent to the data sources. So you could go into Power BI, Query Editor, go to Query Tools, Query Diagnostics, and try to capture the native queries used there. Or you could hop over to your data source and look at whatever logging or tracing capacities it has to capture native queries, and then capture that native query, and then mentally reverse engineer it to see which pieces of your Power Query expression are reflected in that native query. And that's how the authoritative way to tell what optimizations and what's been query folded. It's not fun. I hope one day that we could see on this step list icons on the right, maybe or somewhere on here by each step that would accurately reflect whether the step is fully folded, partially folded, or not folded at all. Because, when for performance tuning, let's think about this for a minute. We've said that order matters. Let's talk a little more about that. I probably want to offload as much processing to the data source as possible. It's designed to process its data well. Let's tell it what we want and let it do what it can with excellence. So we would prefer to order the foldable steps first as a general rule. And then those steps that aren't going to be folded, which means streaming is going to take place between them, we would prefer to order those steps so that the steps that reduce data, get rid of data, occur before steps that need to internally buffer data. This leads to the question then of, well, which steps are foldable? There's no authoritative list I can point you to that answers that question. And remember, as we talked about a little while back, there are a number of variables involved: mashup engine version, data source, data connector. So to performance tune, to really understand which steps are folding, you can kind of make some good guesses, and then to check, you may have to go look at the native queries. And then, unfortunately, with determining which steps internally buffer when streaming's in play, again, there's no authoritative documentation to point you to. However, you may be able to get a pretty good intuitive sense by thinking about what that particular function does. Table sort rows, well, to sort rows, unless you know the data is already sorted, you're going to have to buffer internally. Whereas a table select rows can process one row at a time without knowing or caring about the existence of any other rows, so it doesn't need to do any internal buffering. Joins, well, there's several different join algorithms, and so buffering may or may not be involved depending on the algorithm. So unfortunately, this is one area where when performance tuning becomes necessary, it gets a little rough, and you have to do some digging and some thinking and some analysis to figure out what's going on. I wish it were easier, and I hope down the road it becomes easier. But there we have it. I mean, we've talked about some foundations of Im. It's immutable, but keeping in mind that tables, binary data, and list data are it's handles that are stored for them, not the actual data. Im streams, Im has query folding, Im let expressions and records are lazily evaluated. Function arguments are eagerly evaluated. There we have it. I hope this has given you a better grasp for some of these key Im concepts. If you'd like to learn more about Im, I'd invite you over to bengribaudo.com. We have a long, ongoing, very deep dive into the Power Query language. Now, if we have some questions or discussion, let's have some fun with it.
You betcha. I'm first in the queue. Thanks, Ben. It's Jeff here again. So, why would we want to put a native SQL statement into the Power BI kind of SQL box if query folding was an option? Is one reason that the SQL statement that we write might be optimized beyond what query folding would provide. That is, we've found a smarter way to do it. So we write the SQL and put that in that, I forget the name of the dialog box, but the SQL Connect box. Can you talk a little bit more to that? Like, for instance, so where I'm working, I believe we quite often write SQL statements rather than use query folding. When would we want to do that?
That is a great question. I think you're onto one case right there where you know exactly what you want to do in SQL. Power Query's query folding isn't getting you there. And so you decide there's a performance advantage to writing my own SQL. No, just to interject on top of that though, when we talk about performance tuning, we don't want to prematurely optimize. So if Power Query is handling it just fine, then maybe it's okay if it's not quite perfect. It's native SQL. But let's think of some other reasons why we might want to write our own native query. Maybe our company has a standard query for this situation. Maybe there's a corporate wiki that lists if you need to pull such and such data, here's the query to use. And we want our Power BI report to follow that behavior exactly. So I don't want query folding. I want to use this exact query. Maybe there's something going on where I need to pull that data from a stored proc, or maybe I need to do stuff with temp tables, things that native query folding won't do. But in general, though, if query folding can do what you need, and it can do a lot, it is great to use. There's not an advantage to writing your own query per se if query folding can do it for you and do it successfully.
I imagine that often the reason we use SQL as worldwide as Power BI practitioners is we just don't know enough about Power Query. And so we're all SQL pros who are into this new world, and we go, well, I don't want to mess with that UI. Or I've tried that UI out on Excel and it's slow as heck, not realizing that the reason it's slow as heck is because it's having to buffer everything because we're trying it out on a bunch of CSVs stored in a local drive. So it must be an education thing, right?
It certainly can be an education thing. And I just point out an advantage, though, of query folding that native SQL can't give you out of the box. And as if I write one Power Query and then reference it from 3 other queries, query folding potentially can think about how I'd have to do that for native query. I'd write one Power Query with a native query, and then I'd have these 3 other queries that reference that one query. So when each of those is executed, everything else has to be streamed, right? Because each of them is referencing a native query and then adding some function calls on top of it, and they're all streamed. Whereas if I don't write that native query in that first query, but instead I let it be full query folding, well, query folding can potentially fold across that first query to the referencing query and fold everything up. So if I have a base data query and then I'm referencing it with a query that just counts the rows from the base data query, if that base data query is a native SQL statement, then all the rows returned by it have to be handed to the table. What is it? Count rows statement in my second query. Whereas if query folding is taking place, then hopefully Power Query will just write a select count star from blah blah blah. So that's something that a native query won't give you. But I certainly have done plenty of writing what is it? Value native query statements in Power Query. I find sometimes I do it because I'm working with such a complicated schema that it is simpler to do it by hand. But that's the situation. I'd say as a general rule, try to use the query folding.
You pointed out a great reason why it might be done is because people have standard SQL statements already, but you could just replace the standard SQL statements with organizational standard Power Query statements, right?
Oh, that's a great idea. And of course, another option is you could try to get that standard SQL statement put in a view and then query fold on top of that view.
Okay.
So more on this. David has a question. I have SQL, or my SQL has a series of complicated joins, i.e. Already solutioned and written. Should I attempt to redo it in some way to invoke query folding? So it's sort of more of the same theme, I'm guessing.
It's a great question. And maybe we should approach it from the cost versus benefits side. If you already have the complicated SQL and you just need to return the rows from it, maybe you just write the native query or drop it in there, right? You've already got it. Why recreate it in Power Query? On the other hand, if you've got this complex SQL statement, which you need to reference a bunch of different places in your Power Query, each of which is doing other things to the data, it might be to your advantage to translate everything so query folding can take place so that that query folding can incorporate each of the additional transforms that need to be applied. Does that help, David?
Seems yes.
Absolutely. So unless performance is a problem, leave it.
Right. It's a cost v benefit deal. Yeah.
Yeah.
Ironically, you won't know.
But see, now that you understand, if you understand what query folding does, you're in a much better position to weigh the pros and cons.
Great.
But ironically, you won't know that it's a problem unless you try the other way, right? You've got no compared to what.
Yeah, 5 minutes versus 5 hours, Jeff. One of those might be a problem.
Yeah. But you need to do both to find out, what the other is like, right?
But isn't there a threshold though, where if I have a Power Query expression that runs, whether it's native SQL or query folding, and runs in 15 seconds, that's probably just fine if it's a report that refreshes 3 times a day. If it's running in 10 minutes, we might need to think about it. If it's running in 5 hours, well, we really ought to think about it, probably.
Can you talk about buffering across queries? Whether table buffer works across queries? I think the answer is yes, but I'm not 100% sure. And maybe the answer is it depends.
Well, it depends on what we mean by across queries. So let's pretend so if I have one query that references another, let's think behind the scenes. In a sense, you could argue that to Power Query, we're not executing one query referencing another. We're just executing one big expression that contains the logic from both of those queries. So in that sense, yes, the buffer applies across queries because we're not really executing one query referencing another. We're executing one query. However, the buffer only applies to a single invocation of to a single expression execution. So if in my Power BI report, I have 3 queries that reference one base query, and there's some buffering going on in that base query, each of those 3 query executions is going to have a separate buffer. It's not going to share the buffer across the 3 separate references. Does that make sense?
It will do when I watch the replay.
Pardon me?
It will do when I watch the replay of this video.
But let's make it more complex. It turns out, though, that it may not be as bad as it sounds, because the Power Query engine or ecosystem may also do some caching that we haven't talked about yet. It turns out that for certain data sources, like I believe SQL Server, but not just SQL Server, the Power Query may cache the results returned from a given native query and then reuse those results in the future when it sees a request for the same native query. This is not guaranteed to happen, but it may happen. And for normal report loading, that cache only lasts across the current, the current execution of the set of queries. So if you go in Power BI, hit refresh, it's only going to last for one refresh. But in Query Editor, those caches can last longer, which is why you see those errors or messages saying that the preview may be 21 days old or whatever. It's that cache in play. So buffering is not going to help you across separate query executions. But that caching may, but keep in mind that caching is only, if it happens at all, is only happening at the native query level. It's not, which would include, by native query, I mean the query sent to the data source, which would include whatever query folding wrote into it. But it's not going to include, it's not going to cache anything beyond that, like what your non-query folded im function calls are doing.
Thank you. So to be clear on something you said earlier, if you were developing a brand new report, populating a brand new data model, and you were equally good at SQL and using the PQ interface and maybe writing a bit of M, you wouldn't do it in SQL. You would, unless you had a really good reason, you would do it in Power Query.
Absolutely. That's the language of the tool. And it gives us advantages because that query folding can adapt based off of how we end up using it. I can write my one base Power Query expression and then reference it from 3 places and know that query folding is smart, may factor in the logic from those references, which it couldn't do if it was a native query. So yeah, I would definitely recommend starting with query folding, but if I already have existing complex SQL, that's a different story. Or if performance becomes a problem, again, that's a different story. I'm not trying to say start by writing your own SQL. So great clarifying question. Thank you.
And before
we have another question, Jeff. We have a question from Jonathan. Do you use source control for your PQ scripts?
That is a great question. If you've tried to source control Power Query, it's challenging because there's not much out there that lets you read and write or see what's inside a Power BI or Excel file as far as Power Query goes, at least not without having the host application running. So you can use an external tool with Power BI and do source control through that, but it has to be running. Earlier this year, I released some PowerShell commandlets that can read Excel files and write to Excel files without Excel being present. And they can also do it for Power BI files as long as the extended metadata feature is not enabled, which means they're pretty much becoming obsolete in the Power BI world as that becomes the default. So that's really the only way I'm aware of to try to do Power Query source control if you're trying to do it without having Power Query installed and running, is to use those commandlets because they can copy in and out of the files. They can do things like you can search across files to look for content. I'm looking for an expression that contains this. It's somewhere in this folder. You can compare Power Query expressions between files, what changed. So if that's of interest, hop over to bengribaudo.com. On the top, there's a tools menu, and you can look at data mashup commandlets and data mashup explorer to see things graphically. Then there's some blog posts on different ways to use it, including how to edit in Visual Studio Code your Power Query from one of those files. I would like to adapt those tools in the future to read the extended metadata format. I hear that Microsoft one day might release the specification for that format, but it is not currently publicly documented, unlike the old format, which is. So I don't know when that will happen. So I feel like this is a big area where hopefully one day we'll see improvement, because to me, to do source control well, you need to be able to do it without having the tool running. It's a great question, Jonathan. Sorry, I don't have a really good answer. Did that help, Jonathan?
He's probably just scrambling for the. Oh no, he's actually dropped off. He's possibly had to go back to work. So we are coming back up to the top of the hour. So do you want to wrap up, Jeff?
Question. Can we squeeze one more in, Phil?
Oh yeah, no, go for it. Yeah.
Excellent. This probably this is about the merge options in M. So there's a couple of different kind of table.merge syntaxes, and one of them obviously isn't buffered, and that's the one that works on sorted data. I realize this because Chris Webb had a blog post about using this merge on sorted data because it's much faster. And I used it, and it was much faster. But later on, when I did something else that threw the data out of order, when I used a normal merge, I didn't get as much data back as I expected. Do you know what I mean by that? Does this ring a bell?
Are you, by merge, are we referring to join or?
Join.
What? Okay. So with join, there's something like 7 different algorithms that can be used. And whether buffering occurs or doesn't occur depends on the algorithm used. So by default, the join is going to auto-detect which method to use, decide by itself. And so it looks at certain things about the data, the table it's being given to make that decision. You could, and hopefully it's going to make a good choice. And like you were mentioning, it may factor in the fact that the data is already ordered to decide what to do. You can always override what it's doing by actually specifying which algorithm you want.
This was an undocumented one that it's kind of weird. It actually gives you all columns from all tables. I just can't, right now, I can't think of what it's called. Maybe I'll continue this offline because I had an interesting experience with it.
That sounds quite interesting. And by the way, the whole join algorithm things, the choice chosen there can also affect multiple iteration. You may see if you're joining between like 2 disk-based files, you may see that Power Query reads more rows from a file than are in the file when you join between 2 of them. And it may be because the join algorithm chosen takes 1 row from the first file and then reads every row in the second file to find the matching row. And then it takes the next row from the first file and rereads every row from the second file to find the matching row. So definitely is something to think about for performance. There may be times where you need to manually override the join algorithm, or you just need to put a buffer in front of it, or put a sort and then buffer. Do some way to, depending on the situation. I'm not saying just buffer it, but if you were needing to performance troubleshoot, that's definitely something to look at. That's a great question.
Excellent. Well, thank you very much for giving up your time. It's probably been great for you to have your head out of your country and in someone else's for the last hour.
Oh, this has been fun, and I enjoy the opportunity to present and the opportunity to do Q&A, and we can call it now, or if you want to keep going, either way is fine with me.
Normally, if you do these things in person, Phil Seamark normally gives the presenter a local biscuit here called Shrewsbury. So you normally get a pack of Shrewsbury's, but you're not getting them this time, I'm afraid. John Powter from the XL World present a while ago, and I think he lives in Shrewsbury, or his wife is from Shrewsbury. So he was in town a few years back, and so he took them home to share them with the family. But we're sending you some mental hugs and some mental Shrewsbury's.
Thank you so much. Thanks so much for having me and for coordinating this.
Oh, no, thanks.
You're welcome.
Nice. All right, well, I think we're going to wrap up there and let everyone go back to off their lunch break and go back to work. It's Friday afternoon here, Ben. So
well, happy Friday.
So it was definitely enjoyable to geek out on a lunch break during the day, and there's a lot to take in there, and I'm looking forward to rewatching the recording. So Jeff, have you got anything else to just wrap up with?
No, I've got no more questions. And I've got work to do.
Awesome. Yep. Well, I'm going to head off now too. So I'll stop the recording, and I'll catch you all next time. Thanks again, Ben, and see you all later.
Cheers.
Thank you all. Thank you, Ben.
Thank you all.